Welcome to today's session where we will talk about what's new with Compute Engine. My name is Gopalan, and I'm a product manager with Google Cloud. With me, I have Alex, and later in the session, Mannan from Snap and Mattie from Shopify. We have a packed agenda where we'll cover a quick overview, go into the announcements for general purpose workloads, where you will hear the latest, as well as hear from Snap, followed by our major announcements in specialized compute and hear from Spotify. Let's dive in. Foundational compute use cases power the world's leading organizations, from underlying applications that power highly available e-commerce sites to the databases enabling your developers and customers with reliable and high-performance experiences. But is your compute infrastructure really ready for the AI and agentic future? We surveyed over 1,400 IT leaders, and only 17% of leaders felt that their current setup can handle agentic workloads. Agents can introduce massive, unpredictable scale to your enterprise. For example, a single user interaction now instantly bursts into hundreds of concurrent, high-velocity tasks. Your core applications and databases hold the data required to fuel these intelligent agents. Forcing these dynamic agentic interactions onto static infrastructure risks performance bottlenecks and cost unpredictability. To overcome this infrastructure wall and to truly bridge the gap between today's foundational workloads and tomorrow's AI agents, we must ensure that we deliver the performance and scale our core systems without ballooning costs. Second, we must focus on building an AI-ready foundation. This means establishing a predictable, reliable environment for your everyday workloads, both general-purpose workloads as well as specialized workloads, and ensure that they are ready to handle the high-velocity, non-linear agentic tasks. Finally, we must align consumption to the workload needs. By leveraging declarative and flexible automation, we can enable an infrastructure that adapts to the needs of the application rather than forcing your engineers to handle the toil of infrastructure management. Now, this infrastructure needs to be able to cater to the foundational workloads of today, as well as the AI and agentic workloads of tomorrow, and CPUs have a vital role to play. When you look at AI workloads, we see three emerging trends where CPUs play a role. First, agent sandboxes that enable running agent-generated code and actions on behalf of users in an isolated environment for inference and RL training loops. This requires massive amounts of compute, varying levels of isolation, and fast startup, where CPUs are a good fit. The next one is doing data prep and data processing, powering large-scale AI training pipelines, data preparation and checkpointing, alongside real-time context retrieval at runtime, requires utilizing extreme network bandwidth and massive local storage. And we have some announcements of that which we are very excited about. And finally, running small model inference on CPUs, serving smaller or quantized models directly on CPUs to maximize real-time throughput, inference throughput, while controlling costs. Now, Google Cloud Compute comes in over here. At the heart of our strategy of Google Cloud Compute Platform is delivering a workload-optimized, TCO-ready, and enterprise-ready foundation for your entire digital estate. This adaptive foundation is powered by Titanium, a key technology that underpins and enables Google to bring innovations in delivering planet-scale services like search, Gmail, and Maps over to the cloud so our customers can run like Google. Compute Engine offers both general-purpose flexible compute as well as specialized compute, while GKE enables automated orchestration, along with features like custom compute classes that enable you to prioritize the exact type of compute and consumption mode that you require for your workload. Hyperdisk enables workload-optimized block storage, where you can independently tune your capacity and performance to the needs of your workloads, and also leverage enterprise data protection capabilities, enabling you to be ready for the foundational needs of today as well as the agentic demands of tomorrow. To take it forward and show how exactly we are workload optimizing our infrastructure, over to you, Alex.
Great. Thank you, Sai. As you just heard, at Google Cloud, we've taken a platform approach to our infrastructure. We've expanded beyond the era of just general purpose computing into the era of specialized, high-performance infrastructure. And to meet this moment, we've been aggressively investing at the foundational level of our infrastructure stack to address the biggest challenge that many of you in the room have today. The first is compute, both on performance and efficiency, data and security. So first, on the compute side, we are providing the industry's most comprehensive general purpose portfolio and an expanding set of specialized instances. Whether you prefer Google's custom Axion CPUs, AMD, or Intel, all of our instances run on a Google Cloud platform with hardware-tuned performance and multiple differentiated levers to reduce your costs and TCO. As application experiences evolve with generative AI, as I talked about, customers have told us their challenge is managing larger and more diverse data sets. Titanium enables 3.2 terabits per second of GPU to GPU traffic to feed massive AI training clusters, and up to 1.6 terabits per second of VM to VM networking traffic. We've also dramatically expanded our local storage offerings with ultra-high density local SSDs, significantly accelerating hyperdisk block storage performance to ensure your compute is never sitting idle waiting for storage. And finally, and most importantly, is security of your IP. Titanium enables support for bare metal and nested virtualization, which are foundational capabilities to run secure sandboxing environments. And to protect all your data with instances that support confidential compute, and then capabilities within Titanium, like the Titanium Intelligence Enclave, which provides hardened hardware isolation for your most sensitive data, like your AI model weights that were trained on Google TPUs. Our approach with Google Compute Engine is a full portfolio of optimized compute for your full workload estate. We spent the last year investing in the portfolio to support everything from application servers, isolated sandbox environments, to massive parallelized clusters. On the left, we have the core general purpose products where we offer the latest generation price performance across your choice of CPU. We've continued to expand our general purpose portfolio with new shapes, specifically for scaling up to larger instances for bigger game servers, larger databases, and give your services more headroom to grow on Google Cloud. Moving into the middle, this is where we solve for specific workload bottlenecks. You'll notice the new network and block storage optimized instances. We've built these instances for workloads like network appliances, parallel file systems, and very large commercial databases that are bottlenecked today on networking and storage. These families give you a dedicated path for high bandwidth network and hyperdisk storage performance. And then we've also expanded the Z series. These are our storage optimized workloads with local SSD that need low latency and massive local disk throughput. And then on the right, we offer the latest NVIDIA GPUs with A series and G series, and an exciting line of Google TPUs, including the newly announced TPU-8T for handling your biggest training jobs, and TPU-8i for low latency, scalable inferencing. First, let's take a closer look at our general purpose portfolio. This typically accounts for the majority of usage and spend for our customers. Historically, Google Cloud has relied on a single N-series family to do everything. But as your workloads have evolved, especially in this moment with the rise of AI, we have made a strategic shift at Google. We've split our general purpose portfolio into two major product lines. We have the C series focused on performance and features for enterprise, and then the N series for flexibility. The goal is to let you optimize for both performance and cost. But the real value is unlocked when these families are used together. You don't have to pick one for your entire environment anymore. By putting your performance-sensitive tiers on the C family, like your model logic and data pipelines, and your cost-sensitive services, such as traditional web servers on N family, you are in control to manage both performance and TCO of your workload. So let's start with the C series. The C series instances are performance workhorses and are the default choice for the demanding enterprise environments. Whether you're running high-performance databases, large-scale game servers, or media streaming, the C family is designed for predictable, high performance at scale. First, with C4, we have expanded the use of Intel's latest Granite Rapid CPU across the entire C4 sizes. This delivers the highest CPU frequency of any instance at 4.2 gigahertz and a major 36% higher performance than the previous generation. C4 is enterprise ready for your AI workloads with support for Intel AMX and the native FP16 for some of those model inferences that Sai was talking about early on. Last year, we delivered C4D, and we've seen incredible customer traction with up to 30% improvement, particularly for those data-heavy workloads like MySQL and Redis. AMD has continued to be the easiest way to achieve both value and performance for your workloads. And then a major cornerstone of our roadmap is Google Axion. Our C4A instances are delivering a 65% better price performance versus some of the comparable x86 instances. Axion CPUs are a modern efficiency play for high-density microservices and web-scale apps with unprecedented value. And then to support your full estate of enterprise workloads, we've backed the entire C portfolio with titanium local SSDs, scaling up to 18 terabytes, and then pairing that with advanced maintenance controls to ensure your critical workloads stay up even during infrastructure updates. And then with bare metal instances now available across Axion, AMD, and Intel, you have the flexibility to run everything from your own hypervisor to very high-density AI agent sandbox environments. So while the C family covers your high-performance enterprise needs, the N series is where a majority of general-purpose workloads run. We have expanded the N portfolio with a goal to make the infrastructure work for you, really balancing global scale with flexibility to optimize your costs. A differentiated feature that Google Cloud provides exclusively on N series is custom machine types, or CMTs. Most providers force you to fit your apps into t-shirt size of vCPUs and memory, which naturally leads to over-provisioning. We've solved this problem with CMTs. You can tune your vCPU and memory to the requirements of your workload. We've updated the N-Series portfolio to help reduce your TCO across a comprehensive set of workloads. On the Intel side, we have N4, which delivers a 20% price performance improvement over the previous generation. Beyond the 42 regions of availability, we support nested VMs on N4 as well. This is a foundational feature for running some of these new AI-enabled experiences where you want isolation. For your throughput-heavy web application tiers, N4D with AMD Turin provides a significant performance jump. For example, we've measured up a 250% improvement on the Nginx benchmark compared to the previous generation. We've also introduced a new 96 vCPU shape. This gives you much more vertical headroom for denser applications without needing to move to some of the specialized families. But the opportunity for many of you will be on N4A with Axion. It's delivering 2x price performance and 80% better energy efficiency versus some of the current x86 instances. Axion provides a path for providing lower TCO while growing your footprint in a very sustainable way. So to see these architectures operating in a global, real-world environment at scale, I'm excited to welcome up Mannan and Saleem from Snap to the stage to share their journey of building and scaling infrastructure on Google Cloud.
Hi, everyone. My name is Mannan, and I lead the compute infrastructure at Snap. So at Snapchat, we believe the biggest opportunity today that is presented by camera is to change the way how people interact with each other. We take pride in enabling our users to just leverage that really strong tool and express themselves, engage with the world, interact with each other, and just have fun doing it. And here are some of the ways Snapchatters engage with the community to really interact with each other. So Snapchat has a really engaged community of more than 900 million monthly active users. And more than 460 million of those use the app every single day. In 2025 alone, Snapchatters shared more than 2 trillion snaps. That's more than 63,000 snaps every single second of that year. And our most important ML, content and ads ranking stack, it processes more than 1 billion events per second. That's massive scale. And we wanted to build foundational infrastructure that can handle that scale and scale well with it. Some of you might know, Snapchat started off as a Google App Engine application. And this was probably world's largest App Engine application back in the days. But obviously, we grew out of it. Now, today, we manage a massive, really dynamic, world-class compute infrastructure that leverages core GCP services like GKE and GCE. And I'm going to talk a little bit about that. So back in 2017, we started our journey to transition into our on-prem, in-house service hosting platform. We call it Service Mesh. Today, Service Mesh hosts more than 1,500 microservices, some small, some large. But they handle more than 250 million requests per second across services on GCP. And to handle that traffic, we provision compute in a number of our GCP projects. That compute is hosted in our more than 2,000 Kubernetes clusters in GKE, and we scale them up to 170,000 plus VMs during daily peak hours. And that amount to millions of vCPUs and petabytes of storage in PD and hyperdisk storage. Here is the high-level architecture of the Service Mesh platform. At its core, it leverages some open-source technologies like Envoy to manage traffic and Kubernetes to do workload orchestration. And all of this is possible due to foundational GCP services like GKE, Google's Kubernetes engine, GCE, and disk solutions like hyperdisk and persistent storage. So Service Mesh provides a centrally managed compute platform as well. So it allows you to handle all the heavy lifting of provisioning compute, scaling it, managing the life cycle of it, performing updates for OS and Kubernetes versions, and so on and so forth. And it also provides a consolidated API layer for compute operations, so platforms like ML and content generation and ads can leverage those APIs to do basic basically they can write applications on top of it. So create applications, update applications, scale them, manage the lifecycle of different states of that application, and so on and so forth. So within the sphere of Service Mesh, let's talk a little bit about our compute strategy. And we kept it super simple intentionally. You would see that in my slide here. On the CPU side, we completely rely on auto-scaling. The traffic comes in, we scale up. The traffic goes away, we scale down. So essentially, we only pay for what we use. I know that was the promise of the cloud, but I've seen that in action at massive scale, and it works. Obviously, there are caveats around here, and we can talk about that as well. But we did invest in some in-house systems to really accelerate adoption of newer generation machines from GCP really quickly. So we consistently bring in new hardware to our infrastructure, test it out in a scoped environment, benchmark performance, see where price performance makes sense, and quickly adopt them. So that kind of system is super critical to bring in latest generation changes that Alex was just talking about. We also regularly audit compute allocations and utilization of resources for workloads. And wherever we see the opportunity to right-size, we do that, so we're not leaving any capacity or resources on the table. And finally, if you talk about machine type specifically, we are very heavy users of C-class and N-class family machines at Snap, and we keep on adopting newer generation of those machine families as well. On the GPU side, though, you can imagine the strategy is slightly different. These are super expensive machines that are hard to get by, so we really had to rely on our reserved capacity, basically capacity reservations to handle the peak load. So we acquire a lot of GPU capacity in our accounts, and we centrally manage it. But we did invest in a very robust virtualization layer on top of our reservations. Without going into the detail, what it allows us to do is to share that GPU very expensive capacity across almost all of the workloads at Snap. So you can imagine an inference workloads coming in, following the daily traffic pattern, following the peaks and trough, but leaving a lot of GPU capacity idle during the trough period. But training can come in, or other batch workloads can come in and fill in those gaps and maximize the utilization. So even though we are reserving that capacity, paying it for the whole 24 hours, but we're trying to optimize the utilization of that. So again, it's all about meticulous planning, forecasting, working with our partners in GCP to secure that capacity, and then consistently right size and enable sharing to minimize the waste. In terms of the machine types, we are heavy users of G2 machines, as well as A100s and H100s. And that all depends on the use case. But we are actively experimenting with G4 machines as well, and we have a plan to accelerate our adoption there. So as I mentioned earlier, we have a multi-layered approach. We use many different machine types, machine families, machine generations based on the need. And we also pick the machines based on workload characteristics. There are workloads that are very latency sensitive. And then there are workloads that can absorb a little bit of like latency hit and gain some price performance. So we really test our workloads against these different generations and different types of machine families, and then pick the one that really makes sense for each workload. Very specifically, more recently, we experimented with C4D, and we ran a bunch of benchmarks and performance tests against our really high latency sensitive workloads in inference and training, mostly in inference and also on the ad stack. And then we are seeing upwards of 28% performance improvement compared to the old generation machines like C4Ds or C3Ds and Milans. So that's massive gain, and we really want to double down on that and then adopt it as much as possible. For workloads that are not latency sensitive, we were able to achieve upwards of 20% price performance gain by leveraging newer generation N machines like N4s. Similar kind of results we are seeing with N4Ds. And the third thing we recently tried is have a mixed fleet of GPUs and CPUs. And that's been becoming a thing for a very diverse kind of like environment. For instance, you might have some inference workloads that can still run on high-end CPU machines. They're like low-end inference models that can still run on CPUs. So we got success in running a mixed fleet of CPUs and GPUs, where we use GPUs as much as possible, but once we hit the wall, we spill over to CPUs. And in that environment, we are also seeing better price performance for our workloads. So higher availability and better price performance by mixing and matching CPUs and GPUs, depending on the workload characteristics, especially like lower-end inference models. I touched on this a little bit earlier, but the core part of our accelerated adoption of newer generation machines is basically like having automation and a framework for rapid experimentation of newer machines and adopting it at scale. On the surface, it sounds simple, but it brings in a lot of complexity and operational overhead for, especially platform teams like us who need to scale it across hundreds of teams. So what we have done in the last year or so is work really closely with GKE team and build this platform. We call it custom compute classes and node order provisioning. What it enables us to do is slide in new machines into our infrastructure, validate workload performances on those machines in a very scoped environment. You can write small amount of traffic to that workload and validate the performance, and then give you central controls through which you can just roll it out across the fleet without doing a lot of operational overhead. So previously, something like this would take us multiple weeks of planning and execution, and it would engage multiple organizations, and it was a huge overhead. So now this technology was a game changer for us. And now we are able to build this automation using custom compute classes and node order provisioner, and we are able to do the same thing with a few clicks centrally, and it can be done in a day or two. So that's massive. So if you are in this space, if you are using GKE, especially if you are using different machine families and types, I would encourage you to look into that technology. It's been a great accelerator for us. And by the way, there's a session specifically on that later today. If you are interested in the deep dive, please check it out. One final thing I want to say here is what this also does is it offloads a lot of operational overhead to GKE team. So if you are operating Kubernetes clusters, you would know how hard it is to provision thousands of node groups, perform upgrades on them, configure priority expanders across those node groups, configure fallbacks, and keep it consistent across the fleet. All that complexity will be offloaded to GKE. So definitely recommend looking into this. And another interesting use case for Snap is peak events of traffic. Like, obviously, we have Black Friday, Cyber Monday. We get a lot of traffic on our ad platform. We have New Year's Eve. And there are a lot of high-stake sporting events. We get a lot of activity on Snapchat application. But New Year's Eve is by far the biggest event in terms of traffic. And you can imagine, as midnight is hitting different regions, people are engaging in the app right on the dot. And we get traffic on that second, upwards of 3x, and even more in some regions. So this is massive traffic in a very short amount of time, and we have to really plan for it ahead of time. So we work with GCP capacity team. We look at our month-over-month capacity growth projections, look at organic and inorganic growth, and we work with them to apply historical multipliers, how much spike we're going to get, and we secure that capacity. So once we have the capacity secured, we figure out which workloads can work with different machine families and different machine generations. We apply multiple layers of fallback for those, so we are not hitting any availability issues. And finally, we run game days for scaling. We actually scale up our infrastructure to the target scale and address any scaling bottlenecks that might come into the picture. So this is a very close coordination that we are doing with GCP team and GCE team specifically over the years. What I would say here is, I've been doing this for almost 5 years at this point, and the progression of how much effort it requires to do this kind of work has significantly reduced from months of planning and execution to now weeks and days of planning and execution. And that is largely due to innovation in terms of the technology that GKE and GCE team has been sharing with us over the years, as well as the acceleration in terms of the capacity landing that they have been doing for us. So that's amazing collaboration there. And then once the time comes, hours leading up to those traffic events, we scale up our fleet, and then as soon as the traffic is over, we revert back to auto-scaling. So just to sum it all up, first off, we are seeing a lot of performance gains, as it was shared earlier by Alex as well, with newer generation Turin machines, C4Ds, N4Ds, as well as N4s. So do check it out, but experiment with it. If you're going from older generation to newer generation, machines may not map one-on-one. There are different shapes and sizes and different configuration changes across generations. You need to test your workload on that, and based on that, make a decision to adopt it. Invest in a really robust experimentation, like machine experimentation adoption framework. Like use custom compute classes, use node order provisioner. Keep on trying out newer generation machines as soon as they come out. compare the price performance, compare the performance with different generations, and then like build automation to really like roll that out using CCC or compute classes. And finally, just want to land that message that GCE VM portfolio is diverse, and that's been catering to almost all of Snap's needs. And we are really excited to leverage that for our future innovations in the Gen AI space and agentic AI workloads that we are currently working on. And that's all from me. And I'll hand it off to Alex.
Great, thank you, Mannan. So what Snap has built is a perfect case study for workload-optimized compute, demonstrating that precision in your infrastructure choice is the most direct path to efficiency at scale. So now let's talk more about our specialized instances. We've engineered our specialized instances to solve the architectural bottlenecks that surface at scale. While our TPUs and GPUs handle heavy model training, these specialized tiers ensure the rest of your mission-critical systems can keep up. First, we're introducing a new network and hyperdisk optimized family, starting at 400 gigabits per second and scaling up to 1.6 terabits per second of networking performance. These products are built to maximize throughput and ensure your databases, security appliances, and analytics engines never have to wait on the wire. We complement that with storage-optimized instances, including two new families, the Z4M and Z4D. By bringing up to 168 terabits of low-latency storage directly to the compute, we're solving the IOPS gap for everything from distributed NoSQL databases to real-time AI systems that require instant access to massive data sets. HPC, more critical than ever as simulation jobs grow in complexity. With the H4D powered by AMD Turin now in GA, we're delivering 192 cores paired with Cloud RDMA to handle your largest scale modeling tasks. And finally, our memory-optimized M4 and X4 families. These provide the largest RAM footprints in our portfolio, up to 32 terabytes of RAM. This is the specialized hardware required to serve enterprise applications to more users. So today I'm going to focus in on network and storage tiers, as these are the primary drivers of making your core infrastructure truly infrastructure AI ready. So since launching C4 in 2024, we've scaled networking performance by up to 16x to stay ahead of the massive throughput requirements of AI and enterprise data pipelines. This trajectory highlights our shift from general-purpose connectivity to delivering the highest I/O performance, ensuring that in 2026, your data moves as fast as your compute. Both AI and core workloads depend on the ability to store, read, and move data as a single high-performance operation. By leveraging larger pipelines, your I/O-sensitive workloads get the dedicated bandwidth they need without requiring you to overbuy critical compute and memory resources. First, C4N. This is designed to give you the same feature set as the C family, but specifically built for your high-volume network applications, real-time analytics, and your databases. For your memory-intensive estate, we're introducing M4N. Historically, organizations had to over-provision cores just to meet memory speeds, which drove up software licensing costs. M4N solves this by focusing on per-core performance to reduce the largest portion of your TCO. And finally, for the ultra-high-end requirements of managed Lustre, we have C4NX. This is designed specifically for researchers and data scientists who need industry-leading throughput. C4NX enables you to scale parallel file with the performance required from the most demanding AI training pipelines and large-scale computing jobs. So C4N, let's talk about that one. This will be the default choice for the majority of your I/O-bound workloads. By hitting 400 gigabits per second and 95 million packets per second, we're effectively grown the networking pipe by 4x. For those of you running telco, 5G stacks, or high-volume security appliances, this removes the ceiling that usually forces expensive architectural workarounds. On the storage side, pairing this with 25 gigabytes per second and 1 million IOPS of hyperdisk performance means your most demanding databases, like those NoSQL or large analytics clusters, are finally fed at the speed that they require. The outcome is a 60% lower TCO by right-sizing the compute and storage resources to unlock the bandwidth needed for your data pipelines. It's a highly flexible shape, scaling all the way up to 192 vCPUs with the option for bare metal. C4N is in preview today, so scan the QR code to sign up and try. We're already seeing super strong traction across the ecosystem with C4N. Industry leaders like NetApp, Ericsson, Nutanix, Teradata are all designing their next generation solutions with C4N to provide foundational performance needed for the next generation of I/O-intensive workloads. And for those of you managing Oracle or SQL Server, M4N is designed to solve the most common licensing to performance bottleneck. We've delivered industry-leading per-core IOPS, throughput, and memory to ensure you get the maximum performance out of every license you buy. We offer up to 26 gigabytes of RAM per vCPU to provide the memory density that's required for these large databases, and that's increasing. A lot of you have told me this week that the amount of memory you need is increasing. So pairing M4N with HyperDisk Extreme delivers 25 gigabytes per second and 1 million IOPS. This really helps optimize your TCO for the Oracle workloads by over 20% compared to other hyperscalers. This shift toward performance density is already resonating with some of our largest customers, like Sabre. The high I/O and memory per core of M4N gives them the flexibility to right-size their workloads while maintaining the performance density required for global operations. Next, let's look at the Z family. As datasets grow, the primary bottleneck shifts away from raw compute to data proximity. We have two parts of the Z family, the database and analytics, and then the AI ML data stores. Let's look at the new offerings within each of these categories. First, we're introducing Z4D. This provides a massive jump in both compute headroom and storage density for your database and analytics workloads. We've packed in 84,000 gigabits of high performance and low latency titanium SSDs with options for standard and high density configurations to give you control over your I/O core ratios. We've also brought the 400 gigabits per second networking to ensure your data movement and ingestion stay ahead of your processing power. Next, to address the extreme data requirements of AI/ML, we've engineered Z4M with 168,000 gigabits of titanium local SSDs, effectively doubling the storage density of the Z family. We've also integrated cloud RDMA into this shape to provide the sub-millisecond transit speeds required for distributed training. And lastly, Z4M is integrated into Cluster Director. This provides a unified management across your compute, network, and storage layer. This allows your teams to manage the entire AI infrastructure stack in a single entity, reducing operational complexity while ensuring your accelerators maintain peak utilization without data starvation. To see the real-world benefits of storage-optimized instances at an unparalleled global scale, please help me in welcoming Mattie Toia, VP of Infrastructure from Shopify.
Thank you so much. It's great to be here this morning. Thank you for waking up early to join us today. I'm Mattie Toia. I'm the VP of Infrastructure at Shopify. And so for those of you who don't know about Shopify, maybe you're not in the retail industry, or perhaps you've never listened to a podcast or watched YouTube videos to see our commercials, we're kind of the brand behind the brand. Shopify is what powers commerce for our merchants and their buyers all around the world 24/7. Last Black Friday, we hit record sales. We had record GMV powering through our systems. Terabytes of database queries being processed during one single day. It really is the peak of peaks that drives our business and the businesses of many entrepreneurs around the world. And Shopify relies heavily on Google Cloud. We've had an amazing partnership with Google and their engineers in order to work together to build the solutions that scale and really work for our merchants and their buyers. In addition to our strong reliance on the amazing compute portfolio that Google offers, there are many other services that we take advantage of in the GCP ecosystem that complement the workloads and really bring the full solution together. We saw our global deployment peak past 3.8 million cores last year for Black Friday, and petabytes of data being processed. And in order to make all of that work, we turned to Google to say, hey, what's the best solution? What's the best machines we can use? What's the best way that we can approach this problem? And this is a conversation that continues over time as new technology is introduced. And so just this past year, we started to incorporate the new storage-optimized nodes into our fleet. Specifically, the Z3s and the Z family machines were used to power the Shop app, which maybe some folks here are familiar with. If you had any packages that were ordered during the Black Friday or holiday season last year, all of the tracking, all of your user information flowed through our new storage system all on the Z3 nodes, and we continue to migrate more to that platform today. And the reason is really it's just a fantastic platform to build on top of when you're designing your own storage systems at scale. It offers the enhanced maintenance options, which really gives you the kind of control that you need when you're dealing with local SSD that has some parameters that need to be taken care of to make sure that your data remains durable and replicated for failover purposes. And the latency and throughput that you get from local SSD is unparalleled. We've seen 2 gigabytes a second random read throughput while not even stressing out the CPUs on those nodes for some of our busiest storage backends. And as I said, we've proved it at scale. Seeing it survive the Black Friday season is no small feat, and we're really excited to continue that migration through the course of the rest of this year. And I'll talk to you a little bit more about what that looks like. So historically, Shopify has been a huge user of MySQL. We had a custom sharded MySQL storage solution. With this, we had many different shards. Now, using the new Z3 storage architecture, we're moving to a distributed SQL database called Yugabyte. This uses quorum-based writes, allowing us to write to multiple nodes at the same time, ensuring the transactionality and performance of our systems. With this new architecture, we no longer are worried about this manual sharding. It's reducing complexity in terms of our design and architecture and allowing us to unlock new design patterns in our application, which really is helping us take the product forward as we have larger organizations managing multiple stores or more complex enterprises moving onto Shopify's platform. Really, this is the storage system for the future for us, and we really are able to do it thanks to the Z family of machines. So some best practices and tips that we've picked up along the way as we've thought about using these nodes and sort of how we've made progress with adopting them into our fleet. Certainly, really think about the considerations of attached storage. We historically had been using persistent disk and hyperdisk, so network storage as part of the GCP compute family. But now moving to local SSD, there were systems that needed to be redesigned to think about how to handle those local disks, taking advantage of actually using this enhanced maintenance policy that Google provides. You know, it's part of the engagement that you have with the team in order to make sure that you're doing the maintenance at convenient times and making sure that your system is bringing in new nodes to support nodes going out for whatever hardware upgrades they need. Another big thing is my favorite phrase, ABC, always be forecasting. With a new dimension to think about with local SSD, we've been updating our capacity models to really think about how we can best provision our fleet as well as make commitments to make sure that we get the best possible price for our performance. And then finally, monitoring and optimization. You know, as I mentioned with the CUDs, they don't, you know, we want to make sure that we're not scaling up too high past them. And then finally, given the fact that we have such an annual season with our workload, we really want to make sure that when the time comes for us to scale, we're well prepared and already have the machines on hand necessary to serve our traffic. So what's next? You know, this has been just such a great platform for us. We have other storage-heavy workloads that we're really going to start looking at to take advantage of the Z family machines. Obviously, we're thinking about our CPU needs. I'm super excited about the Z4D machines that have just been announced with the higher CPU ceiling that'll complement this, you know, really large amount of attached storage that we have with our nodes. So that's looking really exciting. Maybe I'll be here next year to talk about that. And then finally, we're looking at better migration tooling for just our internal systems. There's a lot that Google does, but of course we all know that our enterprises and our businesses have our own sort of specialized needs, and our engineers are always working hard to think about ways that we can make that transition better. And with that, I will turn it back over to Sai to finish us off. Oh.
And there's one last thing. Rounding out our specialized portfolio based on titanium, we offer bare metal shapes. One of the key things over here is the new one of C4A Metal Preview. This is perfect fit for Android development as well as automotive simulation and more. And you know, customers are already taking advantage of C4A Metal. As you can see some over here, enterprises like Qualcomm are championing Axion C4A Metal instances because they provide 1:1 physical to virtual environment that slashes validation times and accelerates the deployment of AI-driven automotive features. That brings us to the end of this session with a call to action. Let's get started. To make it easier for you, we have a couple of things that we are offering for you, a free assessment of your infrastructure environment, as well as a free consultation. To continue your journey, I would encourage you to take advantage of these sessions that are coming. And please, your feedback is greatly appreciated. Please do fill out the survey. Thank you so much for your time, and have a great rest of the day.